Okay, very good. So I'm very happy to, and we are all very happy to have, Dorsa Sadigh here from Stanford. She has done some amazing work at the boundaries of control, machine learning, reinforcement learning, and she has received many awards. She was graduated from UC Berkeley, but she didn't want to travel too far, so she joined Stanford. And today, from far away, she's going to tell us about all sorts of amazing stuff she's doing. The floor is yours.
All right, thank you so much. Thanks for inviting me, and thanks for the kind introduction. So I'm Dorsa, really excited to be here virtually, seeing you all virtually. And my research is in the space of robotics. And in general, I'm very interested in developing algorithms for autonomous systems and robots that can safely work with people. So I'm very interested at this intersection of human-robot interaction and what can we do algorithmically in human-robot interaction. So today what I'd like to do is I'd like to take a perspective of bringing machine learning and problems in interactions closer to each other and think about how machine learning can help us develop better interactive systems and how we can learn from interactions for purpose of robot learning. So I have a number of slides. I don't need to go through all of them. Feel free to just jump in, ask questions in the middle, and we can just have a more informal discussion. All right, so let's just get into it. So if you think about the field of robotics, over the past decade has seen quite a number of advances. And we've seen robots like the one on the left. So this is from Boston Dynamics, where this robot is doing parkour. There are fancier videos these days from Boston Dynamics. And then the robot on the right is a shadow hand that is from OpenAI, and it's trying to basically move a block from one configuration to another configuration. And I just wanted to show two videos of robots from industry, so not even academia, industry. And we've seen a lot of these advances because we have really good controllers. So the robot on the left uses a lot of interesting control theory underneath it. And then the robot on the right is using machine learning, using reinforcement learning as part of its algorithm for moving this block and doing this complex manipulation task. So now that we have finally got to a point that robotics is at the stage that it can do things for us, I think this is a good time to start thinking about interactions with humans, right? This is finally a point where we can think about intricate and long-term interactions between humans and robots and autonomous systems in general. And we're starting to see some of these, right? We see autonomous cars interacting with humans and human-driven cars. We see service robots or assistive robots, these types of robots are used by users for helping them move objects around, helping them feed themselves. And in general, we're seeing more and more robotics in our everyday lives. And that kind of introduces a whole set of questions of how should these robots interact with people and what are some new challenges that comes up when we think about interaction between agents. So when we think about interaction, the first thing that might come to our mind is, well, human-human interaction. Humans are really good at this, right? They easily come to each other's spaces and they collaborate and coordinate with each other on complex manipulation tasks. And a good question to ask is, how do we think about interactions between people? How do we formalize how two people try to cook together or move a table together? So one common paradigm is to bring in two people together, say, well, there is a task in the middle. It could be a collaborative task or it could be a competitive task. And one way of going about modeling interaction is this idea of theory of mind, which basically says, well, each one of these agents is going to have some sort of model of the opponent, some sort of representation of how the other agent is going to act in this world. And then we can even go further and think about the fact that the opponent thinks about remaking decisions, and there is this game theoretic interaction that goes on between the two agents. And this idea of modeling interaction in this particular game theoretic way is not new, right? This has been around forever, and every field has a name for it, right? We're trying to find an equilibria here. In human-robot interaction, one can call this theory of mind. In reinforcement learning, in multi-agent reinforcement learning, this is often referred to as opponent modeling. In natural language processing, this is very related to the Rational Speech Act. So this kind of idea shows up pretty much everywhere. And in all of these fields, we very quickly realize this is incredibly difficult to do. Now, why is it incredibly difficult? The reason it is difficult is I need to have this belief representation over my partner, over my partner's states, over my partner's policy. And even you could go further, belief over belief of my partner's states is even infinite dimensional, like I can't even represent that. So this type of recursive belief modeling type of ideas can blow up fairly quickly. So how do we solve it? Well, the common approach in all of these fields is that, well, we're going to approximate this somehow. So one way of approximating is to just cut the game at some time step, at the first time step, at the second time step, and do some second order theory of mind. And that's a perfectly fine approximation to do. Like solve it as a stackable game or as a leader follower game, as opposed to the full game. And this is a very, very common paradigm when it comes to human-robot interaction. So we don't worry about the full game. We kind of like at the first step, we assume that we have a human. That human has a model of the robot's capabilities and what the robot can do. There's quite a bit of work that goes into that. Like how do we think about building better robots so that the human can have a better model of the robot? There are ideas around legibility and explainability that goes into kind of this category of work. And then there's kind of this other paradigm that the robot tries to build a model of the human, and a big chunk of robot learning is actually focused on that. So how do we look at humans' demonstrations or data collected from humans, and how do robots build these models of what humans do or what humans would like the robots to do? So in the second part of the talk, I'm going to talk a little bit about this. But for a moment, let's think about this interaction a little bit more. So as I'm arguing, this type of theory of mind modeling is pretty common. And is a thing that we actually used in our own work in 2016, where we were looking at autonomous cars and human-driven cars and their interaction. So you can think about an autonomous car really as a robot and a human-driven car as a human. And what we looked at was this interaction between autonomous cars and human-driven cars. And the way we modeled this interaction was using this game theoretic type of perspective. So our approach was, well, we have an autonomous car, let's say that's the orange car, and then the policy of the autonomous car is going to be an optimizer of some sort of reward function for the autonomous car. And that should be a function of state and actions, which is usual. But what we were basically saying was this autonomous car needs to model the human-driven car, like that is in its vicinity, and think about how its actions influences the human-driven car. So what we did was we brought in this idea of policy of the human-driven car in the reward function of the autonomous car. And then very, very good question to ask is, how do humans drive, or what is this human model? And in this particular work, what we looked at was we modeled humans as agents who are approximately optimizing their own reward functions. So we model human agents as reward optimizing agents. And then we just try to learn what these reward functions are. So there are a lot of interesting research questions in this work, but the quick thing that I want to just mention here is that this game theoretic type of approach kind of works. It is slow, but it kind of works if you approximate it. And for example, in this case of driving, we started seeing very interesting behaviors for our autonomous cars. For example, we started seeing a lot more interactive maneuvers. So one example was, if I have, let's say if this car is autonomous, this white car is autonomous, our vehicle, when it wants to, for example, change lanes, it starts considering its interactions, its game theoretic interaction with the human-driven car. And it started nudging in to see what are the effects of nudging in and if it can influence the human-driven car to slow down and make room for it. And this was as opposed to a very common paradigm that was used in autonomous driving at the time, which is basically just build an autonomous car that does the driving right and not worry too much about interactions. So here's an example of that, right? Like I have a Waymo car, it wants to change lanes, it's in an exit lane, it's signaling, doing everything right, but it's not being very interactive, right? It doesn't consider its interactions with these vehicles on the left, and because of that, it needs to exit and come back around and try again, which is not that ideal. So the problem that this vehicle has here is it is going for functionality of the autonomous car and not as much about the interaction of the autonomous car. And I think that's a mistake that we often make in robotics, right? Like robotics is all about building autonomous systems that can do the task right. And a lot of times people don't think about them as interactive agents and think about their functionalities in isolation. And that's kind of dangerous because if you think about the functionalities in isolation, you don't really consider these more interactive type of maneuvers that are really needed for achieving this task. All right, so that was my quick spiel about theory of mind, right? So theory of mind is a nice way of modeling interactions. We have used it, people use it in human-robot interactions all over, and it's a perfectly fine way of modeling interaction. But today what I'd like to do is I'd like to talk about an orthogonal perspective to theory of mind. I actually don't want to talk about theory of mind. I want to talk about something different. And the reason I want to talk about that is that, sure, a lot of interactive tasks are kind of like playing chess or this interaction between the two vehicles that I just talked about. But there are also a lot of other interactive tasks that have nothing to do with playing chess, that have nothing to do with this theory of mind type of modeling. Like imagine two people like Alex and Bob coming together here, trying to build some sort of structure together. Like in this collaborative task, I really don't think Alex here is saying, well, I wonder what Bob's beliefs over what my policies are, or I wonder what Bob's beliefs over my state is, and let me try to compute that and then approximate it and then collaborate. Like, I don't think that is what people do. And actually, at least like one thing I know about humans is that they're bounded rational. They don't have even the ability to keep track of these high dimensional beliefs. And what I think is happening is that people are really good at keeping track of much lower dimensional entities that is sufficient for achieving this task. And I think that is pretty amazing, right? Like you bring in two humans, tell them move a table together, build a structure together, and they can just like immediately do that, even like through implicit communication, not even using language. Blindfold them, tell them not to use language, they can still move a table together. And then have two robots to try to do the same thing. It's an incredibly difficult task to do with two decentralized robots. So what is it that humans are doing? Like I think this was a question that we had for a while. Like, what is it that humans are doing, and why is it that they're so good at like collaboration and interactive tasks? So our hypothesis here is that what is really happening is that humans are really good at capturing a shared task representation or a low dimensional representation of the partner policy. And what one can give a name to that could be really like the sufficient statistics needed for the task. Like it's kind of approximation of that sufficient statistics, but humans are just like really good at picking that up. And yeah, we often have like more explainable names for them. Like we say, well, what is the role? What is the leading following role? Or what is the intent of the human? Or what is the goal of the human? And at this point, you might say, well, what is the big deal, right? There's quite a bit of work in trying to do belief modeling over intent. Like people do that all the time. Like what is the big deal here? Well, the thing I'm arguing is not to do belief modeling over like 5 intents. What I'm suggesting here is let's figure out what is the space of intents that we need to work in. Like what is that space of low dimensional representations? I can call it intent, I can call it whatever I want. But can I figure out that space like in the same way that humans are able to do? So this kind of motivated us to move further and think about building low dimensional shared representations. And actually, they don't need to be shared. I need to remove the shared here. Sometimes there are shared representations. Sometimes the agents have different observabilities and there are specific representations of the other agent or the opponent. So they're not necessarily shared representations at all times, but they are low dimensional. And I think that's very interesting that humans are really good at capturing these low dimensional representations. And what we were thinking was, can we build robots that are able to capture these low dimensional representations that kind of capture the interaction and can actually change over time? So motivated by this, what I'd like to do for the rest of the talk is I'd like to spend a little bit of time thinking about this idea in some number of interactive robotics tasks and how we can learn these and influence interactions using this idea of latent representations or latent representations of the other agent or latent intent. And then if I have time, I will, at the end, like for the second part, I would like to talk a little bit about learning from interactions. So this is more of learning so we can interact better. The second part is learning from interactions. All right. So let's just get into it. So when we think about some of these interactive tasks, I think the interesting characteristic of these interactive tasks is that these other agents or robots, or like just another human that we interact with, they're often non-stationary. And what that means is that they can update their behavior in response to the action of the ego agent, the robot agent that is acting in this world. So remember the car example I was giving, right? So going back to this car example, if I put an autonomous car like in a world, like people are going to change their behaviors. If my autonomous car is like nudging in front of this other driver, if this other driver was going 60 miles per hour, it's not going to continue going 60 miles per hour. It's actually going to slow down. So robots are actually influencing the policies of other agents, and that is something that we really need to capture as we're moving forward. So let me start with an example for that. So how do we go about that? So imagine that I have two robots. I have a learning robot. So that's my ego agent. That's the robot on the left. And I have another robot. This is the other agent. And the reason I'm calling it other agent is it could be an opponent, or it could be a partner. So I'm not like specifying that this needs to be a collaborative task or a competitive task. And they're trying to play a game of air hockey together. Okay. So what is happening is that this other agent has a policy, the robot has a policy. This policy is often high dimensional. And what that means is this robot has 7 degrees of freedom. It either needs to control like the joint angles of all those 7 degrees of freedom, or it needs to do like some sort of end effector control, figure out like, or velocity control, right? So figure out what is the velocity that it should push the puck so it doesn't fly, the puck doesn't fly off the hockey table, and it's actually right and it does the task like correctly. So the policy of the other agent is often high dimensional. But kind of on the surface, what it is doing is it's really pushing the puck either to the left or right or center, okay? And the ego agent doesn't really have access to any of that, like doesn't really have access to that high dimensional policy or kind of this low dimensional view of it. But just as an understanding, what's happening is that this other agent is going to push the puck towards some direction. And as it does that, this ego agent is going to observe a trajectory, and the trajectory is going to be a sequence of state in its own actions and the reward that it gets. And the reward is if it blocks the puck, it's going to get some reward. Otherwise, it's related to the distance to the puck. So that's the reward that it gets. And as we're saying, well, other agent, it's not a learning agent. It follows a policy. And that policy here, I'm hand coding it. And that policy in this case is push the puck towards a direction that wasn't blocked before. So if you push the puck, like this other agent, if it pushes the puck to the right and the ego agent blocks it, then it's going to change its policy and maybe pushes it to the left there towards a different direction. Okay, so I'm representing that using this F function. So what we're proposing here is we should learn a low dimensional representation of this other agent's policy. And the way we do that is by using kind of like an autoencoder type structure, where we look at a sequence of trajectories, an episode, a sequence of trajectories of these agents playing, and then trying to encode that to a low dimensional representation. Let me call that ZK. This ZK is really like an estimate of this Z. It's not the true Z, it's my estimate of what that Z is. So it should really be Z hat K, but just to make the notation a little bit easier, I'm just calling it ZK. And what this ZK is,
what is K?
So it's a K episode. So we're training this episodically. So so like I'm looking at a past sequence of trajectories, an episode of trajectory, and that particular episode, I can encode that to this low dimensional representation of my latent intent at that episode, and it gets updated. So
Z is basically just a vector. Is that it?
Z is a vector, and it's trying to capture like a latent representation of the other agent's policy.
Okay.
And the reason it's capturing that is actually this loss function. So what it is trying to do, what we're trying to do is we're trying to train an encoder and decoder here, where we look at a past trajectory, and based on that past trajectory, we're trying to predict what the next trajectory looks like. Is that?
Yeah, makes sense. Yeah.
Okay. All right. Yeah, and through that, we are learning this low dimensional Z, and all this Z is capturing is really a low dimensional representation of the partner's policy. And again, like remember, this is orthogonal to me trying to build a belief structure over that high dimensional policy of the other agent. I'm forgetting about that high dimensional policy and what that is. I'm basically trying to figure out what is a representation of the low dimensional policy. And best case scenario, this low dimensional policy should capture left, right, middle, right? Remember, left, right, middle were the three things that the agent kind of at the high level was doing. And I'm not telling the ego agent that you should capture left, right, middle, right? I'm just allowing it to directly learn that by capturing the C. And once I have that, right, like once I do this representation learning type of component, then I have a model, I have a representation of my partner. I've done my opponent modeling component. And then what we do is we kind of integrate this component of representation learning along with a reinforcement learning agent. So what we do is, well, we say at the end of the day, my ego agent, my robot is supposed to play air hockey in a way that is good and wins and does the task right. And that is our goal. So we try to maximize for that goal, try to maximize the expected reward. And this expected reward is going to be an expectation over policy of my ego agent, which is conditioned on how is it that the other agent is playing. And how is it that the other agent is playing is captured by this Z, this low dimensional representation that is my estimate of Z that comes from representation learning. And by doing so, what I can do is I can react to the other agent. So there are really two components here. One is this reinforcement learning component that is basically trying to figure out how to do the task, how to play air hockey. And this reinforcement learning component is conditioned on my representation of the other agent. And where does that come from? That comes from this representation learning. And they kind of feed to each other. They're trained at the same time. I get a representation, I do a run of RL, I get my policy, I get a new episode. And then based on that, I train my representation learning and keep going forward, okay? So we call this our algorithm learning and influencing latent intent, or Lily. And let's just see how Lily works on this game of air hockey. So if you look at this game of air hockey, so the way we define reward is that if the ego agent blocks the puck, we're gonna get a reward of +1. And then if the ego agent blocks the puck to the left, we artificially make the game so you get a higher reward. We just say, oh, you're going to get a reward of +2 if you block the puck on the left. We are artificially making this so the ego agent really likes to block pucks on the left. Okay? So if I train state-of-the-art reinforcement learning, let's say soft actor critic, what happens is that after 2 hours of training, my soft actor critic, the thing it learns is that I should be able to block a puck if I just go to one direction. So it always goes to the right here because it figures out if I go to the right, then I block the puck sometimes. And I don't have a model of the other agent. I have no idea how the other agent is acting. So because of that, like the best thing I can do is to always just go to the right. And then eventually after like 4 hours of training, what happens is that it realizes it gets more rewards if it goes to the left, if it blocks the pucks on the left. So it just learns to always go to the left. So our soft actor critic agent always goes to the left. So it starts blocking it on the right first, then eventually learns that, oh, I should actually go to the left. That's better in terms of reward. And this is a success plot. So not a reward plot, success plot. And if you always go to the left, you're going to get lucky like 40% of the times. And based on that, you can block the puck 40% of the times. But if you're using our algorithm, Lily, what ends up happening is that because the agent has a model, again, a very scalable and low dimensional representation of the other agent, it's able to kind of predict where the other agent is pushing the puck. And based on that, it can just go there and block the puck, like no matter where it is pushed. So in terms of success rate, we're going to get like success rate around like 80%, 90% blocking the puck successfully.
So there is a question actually in the chat. Do you see the chat or should I read it?
Can you? Yeah, can you?
Yeah. So how do you choose the loss function for your representation learning if that choice related to the interaction optimization?
Yeah, that's a very good question. So so let me go to this slide real quick. So the way we are looking at the loss function for the representation learning is here. So it's not a reconstruction task, it's a prediction loss. And basically the loss says, hey, I get like a previous trajectory and I should be able to, like, basically the only thing that is missing from the previous trajectory to be able to predict the next trajectory should be a representation of what the policy of the other agent is. And I want that representation to be low dimensional because I want to figure out what is that sufficient statistic that is needed for doing the task. So that's why I end up learning just the enough information that I would need to have about the other agent to be able to predict what will happen next. So that is why the loss is a prediction loss. Because like I only need to know what the other agent, what the opponent is going to do to be able to predict. And it's enforcing learning like the lowest, like the minimal information almost about the other agent. That would be enough for me to achieve the task. So that is the loss for the representation learning component. But there's also this other reward that we are optimizing from the perspective of the ego agent. So the ego agent is optimizing the reward. And based on that, that kind of affects the trajectories that are going to be fed into this representation learning component. So it's almost, although like the loss of this is just a prediction loss, like based on the data that is going into this, these data are guided by the reinforcement learning objective of just like doing the task right. So they kind of like feed into each other. So kind of in an implicit way, this Z is going to be the Z that is really useful for doing the RL task, which is blocking the puck.
So you have H episodes, right?
Mm-hmm.
So during each episode, there are going to be multiple trajectories, right?
During each episode, so
what happens during each episode?
Yeah, so during each episode, the policies are fixed, so they're not changing, right? So for each episode corresponds to like a trajectory that we see for this. Yeah, so let me. Yeah, so here is like, actually H is really the length of that episode. So, but during each episode, we're looking at a sequence of trajectories of this other agent, of kind of the interaction between these agents. And the policy of the other agent is fixed, right? It's decided to push it to the left, it's going with pushing to the left, and you get just a sequence of state and action. So each episode is just really a trajectory, kind of like time series data of like what just happened in that interaction.
And then when an episode finishes, what happens?
So when an episode finishes, right? So that is when a run of so once you get this data, right? Like you learn a representation Z. Based on that representation Z, you are doing a run of RL, and a run of RL is going to tell you what your ego agent should do next.
I see.
And then you go to the next episode.
I see. Okay, so basically the policy of the ego agent is going to change.
Yeah, exactly. That's how the training works. Yeah.
Right. Okay.
Yeah. So let me go to this. Where was it? Yeah, this slide. Yeah. All right. So basically, based on this type of intertwined training of RL and representation learning together, we are able to learn a low-dimensional and scalable representation of the other agent and use that in an RL loop to basically coordinate and collaborate better in this setting. But the thing is, we could actually do a little bit better than this. And by that, what I mean is going back to this slide, right? What we're doing here is we're maximizing this expected return within an interaction, and that allows us to kind of react to the other agent. But I can actually optimize this expected return across multiple interactions. So instead of worrying about the reward function for like one episode of like, oh, I just need to block the puck in that one episode, I can actually make my rewards to be expected return across multiple interactions. And the useful thing about that is I can, by doing so, I'm not just being a reactive agent that just collaborates and interacts with this other agent. By doing so, I can influence the other agent to respond in particular ways that are useful for me. So what does that mean? So going back to this air hockey example, remember I made this example artificially. So my ego agent really wanted to block pucks on the left. My ego agent really preferred to just do things on the left. Maybe it was better at it. Maybe that is what it really wanted to do. And what I'd like to do is, if I'm getting more rewards as an ego agent, if I'm getting more rewards on the left, then if I can get the other agent to push the puck more often to the left, that would be really cool. That would be really awesome. And what this optimization basically does is it basically tries to do that. By optimizing the reward across multiple interactions, you're actually able to influence the other agent to push the puck more often to the left, because that is how you're going to get more rewards, by just going to the left. And that's the behavior that we are seeing with Lily, with this influencing idea of changing the objective of RL to be across multiple interactions over 4 hours of training. So in terms of success rate, right, like if I have this influencing incorporated, success rate is going to be similar to the case with no influencing. Maybe it takes a little longer to train, maybe. But at the end of the day, it's around 90% success rate. Like if you push the puck no matter where, I'm able to block it because I model the opponent's policy. But the interesting thing that we get is with influencing, we can get the other agent to push the puck more often to the left, like 41% of the times, as opposed to the case that the other agent is kind of uniformly pushing the puck to the left, middle, or center. And that is, in general, I think, very interesting because you can think about more long-term societal scale objectives, and it would be cool to be able to influence and incentivize other agents to act in specific ways that are either better for you or better for some long-term societal scale objective in collaborative and coordinative task. And I'm showing this in that air hockey example, but what I'm really thinking is we have like another thread of work, which is around traffic, and you're looking at kind of some of these more long-term objectives like traffic congestion on roads, and you're looking at how autonomous cars can bring down congestion when we have these larger traffic networks. So I'm thinking some of these ideas of influencing could also be used in some of these other domains. So I understand I'm just showing air hockey here, but the idea of it could be really interesting to take to some of these other fields. All right, so let's just summarize the key takeaways here. So the key takeaway here is that we're looking at these human partners, and these human partners that we are interacting with, they're often non-stationary, right? The moment I put the robot in people's world, the moment I put an autonomous car in people's world, their behavior is going to change. And most of the prior work usually assumes that I have a fixed policy of the human, I just go with that. But humans are not fixed, they're responding, they're acting, they're being influenced the moment you put an autonomous agent or robot in their world. And that non-stationarity makes reinforcement learning in general very difficult, right? Reinforcement learning in non-stationary agents can be a very challenging problem to address. So taking that into account, what we're looking at is we're trying to learn low-dimensional representations, latent strategies that allows us to have a more scalable and more manageable way of addressing this non-stationarity in multi-agent interactions. And our algorithm, Lily, is basically trying to do that by learning these latent strategies and furthermore reacting and influencing them over kind of these more long-term interactions. All right. So that was this idea of learning and influencing interactions. What I would like to do for the rest of the time, I would like to kind of flip this a little bit and try to think about what we can learn from humans, right? This was about, like all I've said so far is an orthogonal perspective to theory of mind that can help us better interact, more seamlessly interact in a scalable way. But at the end of the day, I'd like to interact with people. And that is very difficult. So even with this air hockey example that I was showing, like we were motivated by people's low dimensional representations of policies. And at the end of the day, we really wanted to do this with real people. And that is incredibly difficult. So training with actual humans, training these deep RL policies with actual humans in the loop is just impossible. Like as you saw, like it was 4 hours of training, the robot was training overnight. I can't just like put a human in the loop of like learning here. That doesn't really work. And then fine tuning with humans, one would think, oh, I would just like fine tune with humans. That seems like a promising strategy, but even that is often very difficult because humans' policies is often fairly different from robots' policies and come from fairly different distribution. So it's a difficult task to play this with actual humans. When we pair up Lily with humans, like we get around 73% success, even like and this is a case where we tell the humans what their policy should be, and they kind of like have a predefined policy. But even then, like we're getting around like 73% success, which is lower than what we get with actual robots. So learning with humans in the loop seems pretty challenging. And that seems like a direction that we should really move in, because if we want to build interactive systems, if we want to build systems that work with actual humans, we need to bring them in the learning loop somehow. And most of the prior work in this domain of learning from humans is really focused on the space of imitation learning. So Basically, the idea of imitation learning is, well, I have a person and I would like to figure out what they want a robot to do or how they act in a world. So maybe I'll get the person to imitate, to provide a set of expert demonstrations. Maybe the person is moving this arm and helping the robot pick up the object, provide expert demonstrations for the robot to pick up the object. And based on those expert demonstrations, then one can go ahead and learn some sort of policy for how a human would like this robot to pick up the object. Or maybe we would go and learn a reward function that kind of captures like how this person would like to pick up the object. Okay, so what is the underlying reward function that they'd like to do? Okay, so that is a very common strategy. We've done quite a bit of work in this domain of learning from expert demonstrations. That's an idea that has been around for more than 2 decades. But the problem with this particular perspective is that finding expert demonstrations is very challenging, right? Like these robots are incredibly difficult to operate. They have like 7 degrees of freedom. Like teleoperating these robots is really challenging. Access to expert demonstrations in general is pretty challenging. So an idea that we have been thinking about is that maybe we should go beyond expert demonstrations. There are many other sources of data that are present from humans, and then humans tend to like leak information all over. And maybe we should try to tap into these many different sources of data and be a lot more active about how we are collecting this data from humans. So just very briefly, like we are looking at a few different directions where we are looking at other sources of data. I just want to mention them and then maybe go deep in one of these directions. So beyond expert demonstrations, one direction that we have recently been thinking about is learning from suboptimal demonstrations. So expert demonstrations are hard to collect, but I can bring in like Amazon Mechanical Turkers to basically teleoperate a robot in a virtual environment. And those demonstrations are often not very expert demonstrations, but they tend to be suboptimal. Maybe they're not doing the task like perfectly, but they're still like pretty useful. So could we learn from suboptimal demonstrations? When we have a mixture of optimal and suboptimal demonstrations, how should we develop confidence measures? How should we develop ranking-based methods to still learn something from some of these suboptimal demonstrations? So that's a direction that we're doing some work around, and I think is a very exciting, interesting direction. And that kind of brings us to this idea of learning from observations as well. So if you think about the field of vision or the field of NLP, the reason we've seen a lot of advances from like deep RL in those and deep learning in general in those fields is the fact that we have lots of data. We have universal language models, and the reason we have that, a large reason for that, having that is having large data sets. And if you think about the field of robotics, we haven't seen the same thing. And a major reason is we just don't have that much data, right? We just don't have that much robotics data or that much demonstration data. And an interesting direction, I think, is trying to learn from these other sources of data, like videos or images or language. What can these larger data sets bring us when we are thinking about building robotics agents or trying to do robot learning? So we're looking at learning from like videos. So if I have people like videos of people like cooking something, like cooking an egg, can I learn something from that for a robot about how to cook an egg, or like what is the common sense knowledge that the robot should have? So I think that's a very rich direction and a very difficult direction to go in. And then, yeah, moving on top of that, we are also thinking about the space of robo-NLP, thinking about language instructions and narrations. What can language instructions and narrations bring in addition to expert demonstrations? And what sort of information are they going to focus on when we are looking at these other sources? Beyond these different sources of data, we are also looking at pairwise comparisons and rankings. So a robot might show you 2 different trajectories and just ask you, like, which one do you prefer? And that's a lot easier than collecting expert demonstrations, because you can just look at these demonstrations without trying to teleoperate a high degree of freedom robot. And we're doing some work around active learning and actively generating these types of scenarios to query people and ask people how a robot should do a task. And finally, a direction that I think is pretty exciting here is learning from physical corrections. So a robot has an embodiment. It's not just an AI agent, right? You can actually move it around. And by moving it around, by providing forces on the robot can try to learn something about your preferences. So this was kind of like a big overview. We are looking at all of these different directions. What I want to dive a little bit deeper in is this idea of pairwise comparisons and how we can actively learn from pairwise comparisons. So what I mean by that is, as I was saying earlier, instead of like getting a person to teleoperate this robot to do various types of tasks, I can just ask a person, like, which one of these trajectories do you prefer? Do you like A or B? And then the human's response to this single binary question is going to tell me something about the underlying reward function that the human has, right? Like the human has an underlying reward function of how this robot should go from this point to the black path here while avoiding the obstacle. And if the person tells me, well, I like B over A, that tells me that the underlying reward function of trajectory B is greater than the underlying reward function of trajectory A. And for the moment, I'm assuming that this reward function is a linear combination of a set of features. We have looked at non-linear versions of this too. The features can still be non-linear, but we're looking at a simpler form of this where it's a linear combination of these features, okay? So imagine that I have three features, right? Like imagine this lies in a three-dimensional space. So then I can assume that my rewards lie in a unit ball, and I can sample from this unit ball to kind of capture what is the space of rewards. And then every question, every query that I ask a user generates a separating hyperplane in this space. And the human's response basically tells me which side of the hyperplane is preferred. Does the person like the right side of the hyperplane or the left side of the hyperplane? So then that's a single question. Based on that single question, what I can do is I can update the weights for my reward function. If the person tells me I like the right side of the hyperplane, I can basically say, well, the left side doesn't matter. I'm going to remove all those points, or maybe I'm going to downweight all those points, and then have a better estimate of where this reward function lies. So that's a single question. The interesting research question here is, what is the sequence of most informative, diverse types of questions and queries that I can ask a user in order to learn their reward function as efficiently and as quickly as possible? Because, like, remember, data is a big problem in this domain. So we formulate this as an active learning problem where we say that, well, what we'd like to do here is to find a set of queries, find a set of scenarios, these P's correspond to those scenarios, and find those scenarios that maximize the minimum volume that would be removed from the hypothesis space. So no matter what the person tells me, if they tell me they like the right side of the hyperplane or the left side of the hyperplane, no matter what that answer is, I'm going to ask for questions that maximize the minimum volume that would be removed from that space. Okay. So this is a very common objective in active learning. It's a volume removal objective. It's a submodular objective. And one can try to use even submodular optimization type of guarantees here to think about convergence of this algorithm under a set of assumptions. But this basically allows me to ask informative, useful questions from the user. And I also have a constraint here. My constraint is that these trajectories, these scenarios that you're generating, they need to be feasible. So they need to satisfy feasibility. I need to run this on a real robot or on a real autonomous car, and they need to make sense. So that is what my constraint is actually encoding. In addition to that, well, of course, humans are noisy, so I'm not going to assume everything they say is absolutely correct. So instead of completely removing the wrong side of the hyperplane, we reweigh them based on a noise model of humans using Boltzmann distributions as capturing humans' noise here. Okay. All right. So this is kind of just an underlying way of doing this task. We have looked at other versions of this, where we are looking at other types of information theoretic objectives like information gain or using determinantal point processes. We have looked at the batch active learning version of it. We have looked at the fact that these questions should be easily answered by the humans, right? How do we consider humans' uncertainty in this objective? So I'm kind of skipping all those details, and I just wanted to show you kind of the big picture active learning problem that we're trying to solve here. And just in that simplest form of active learning, right, let me just show you how that works in practice on a very simple 2D simulator. So here, after 0 questions, this vehicle, my autonomous car, the orange car, doesn't really know what to do. After 30 questions, it learns how to keep heading. And then after 70 questions, it learned how to do collision avoidance and keep heading and just stay within the lanes and just generally drive in this simple 2D simulator. And I think that is actually pretty interesting because I'm not using any demonstrations. These are like 70 binary questions, and I've just been very careful about which 70 binary questions I'm asking. But it's actually pretty useful to be able to do this in this robotics domain. In general, I think active learning in a lot of like AI applications has made quite a bit of advancements. I feel like one of the common complaints to active learning is, oh, if you were to do random sampling, like and active learning, like both of them would perform fairly similarly. There are often like these plots when you're looking at active learning papers where the gap is really small and you did active learning and it performed a little bit better. But I really think robotics is a field where active learning can make a dent, can move a needle, because it is like 70 questions versus 75 questions actually like matter when you're bringing in a person to the lab to do a user study. So let me show, like for example, we tried this approach in a work with folks at Caltech where we were trying to learn people's preferences, like for people's gait preferences when they're walking using these exoskeletons. Like here, 70 questions versus 75 questions actually matters. So we're bringing in a user here, we're affecting them, we are basically providing these probes to the person. We need to do that in a safe way that doesn't hurt the person. And also we need to be careful about how many questions are we asking, how many times are we probing the person. So I do really think like active learning can move a needle in robotics and maybe in some other AI fields, like maybe like if you were to do random sampling, that would have been a lot easier and the gap is not that large. But in this particular field, I do think it is important to be a lot more careful about what type of data we are collecting. So yeah, to summarize kind of this part, so the example that I showed earlier, this driving example, this was assuming that the reward function is a linear function of features. In a recent work, we are looking at nonlinear reward functions. Specifically, we are looking at using Gaussian processes. So the reward is represented by a Gaussian process and using very simple features. So we're still using features in this case representing shot speed and shot angle for a robot that's trying to play a version of mini golf, like pushing this golf ball to any of these targets based on humans' preferences. And then even in the case where we have Gaussian processes, one can try to go through this active learning loop and optimize for information gain. There's a bit of more details that goes on here, because as you do your updates based on the responses that you get from the human, then your distribution, your posterior, is not going to stay the same as your prior. So you have to make a set of approximations to approximate the problem as a Gaussian process and keep going through the loop of active learning. So there's a little bit more detail here, but one could actually do this approach with nonlinear reward functions. And here we actually show that if you use a linear reward functions with those simple features, you're actually not able to achieve the task. You can't like push the golf ball to any of the targets that you'd like, because our features were really simple. Our features were shot angle and shot speed. So if you're optimizing shot, like a linear function of shot angle and shot speed, you're always going to push for the corners. You're not going to be able to do the coverage over these targets. But if you use a GP reward, you would be able to basically push the ball into any of these targets that could be preferred by the person. But again, by just a set of queries to the user, no demonstrations were needed here. And yeah, as I was saying, one could also apply this to the setting of using these exoskeletons and learning humans' walking preferences. All right, so let me just quickly wrap up. And I wanted to talk a little bit about this physical interaction, but maybe I'll just mention it. So the idea of the physical interaction is you can physically move the arm, and by physically moving the arm, then you can kind of like learn humans' preferences here. And here we are looking at a task where you have two robots that are carrying a grocery bag, and basically they're trying to help you unpack the grocery bag. So you're placing the bag on the table, and maybe they're going to place the bag like on the blue region, but maybe you have a specific preference that the robot doesn't know, which is that maybe there's water here and you really don't want the bag to be placed on the blue region, and instead you want the bag to be placed on the green region. And at the same time, there are a few other like preferences that the robot is aware of, like the fact that it shouldn't squeeze the bag too much, or shouldn't spread the bag too much, it shouldn't hit the obstacles, and so on. And what we are looking at is you're looking at a setting where the robot is following, let's say, these black trajectories to start with. But if a person comes in, oh, I should have just let that play. If a person comes in, a person is going to provide pushes on the robot, and based on those physical actions that the person is putting in, then the robot should try to update its reward function. And specifically, we're looking at a setting where you're providing a sequence of these pushes and pulls. So not a single one. So you correct it, and then the robot starts like updating its trajectory and updating its reward function, and comes up with an updated sequence of trajectories that it should follow. And maybe that is not perfect. And you keep providing these sequence of corrections that are actually interdependent. They're not dependent corrections, they are interdependent. And we are looking at how to learn from these sequence of interdependent trajectories to be able to learn a reward function. So that's just more of the problem statement. I'm skipping how we go about it, but one can basically do that. Let me go here. All right. Okay, so just to summarize, what I've been talking about so far is first thinking about interactions a little bit more carefully, and an orthogonal perspective to this idea of theory of mind modeling, a scalable way of learning low dimensional representations to have better interactions with other agents. And then in the second part of the talk, I'm talking about how we're bringing humans in the loop of learning. And then there are kind of two core ways that I think are interesting here. One is how do we actively collect data? How can we be more careful about the type of data that we are collecting? And then the other one is just tapping into many different sources of data that are available and trying to build multimodal representations that can help us learn from interactions with humans, from data with humans. So just to wrap up, the one direction that I think moving forward would also be pretty interesting to consider is how these interactions with humans or with other agents in general evolve over repeated interactions. And I feel like that is also pretty understudied, right? Like, as I was saying earlier, a lot of robotics work doesn't really consider humans or interactions. It's all about building a robot in isolation. And then, like we see in autonomous cars, the moment you put that on a road, you realize you should have considered interactions to start with. And that is when you start considering human models and interactions. And I feel like a lot of interaction work is also just all about single step, one step type of interactions. It's not really about long-term interactions that you see between different agents. And I think that's a very interesting direction to go in. So imagine in the case of autonomous cars, right? If you have a car that is nudging in front of another driver, and by doing so, it is kind of like cutting in front of it and changing lanes. Sure, this driver estimates this driver being a timid driver that's allowing it to do this lane change maneuver, but this driver might get really angry afterwards and try to like come back around and get ahead of you. And we don't really study that, right? Like, we don't really study how our behaviors change over more long-term or over repeated interactions. Another example of that is when we see our interactions with autonomous cars. So this is a picture from San Francisco, and I've actually like experienced this myself. So when I bike in SF, I see all these vehicles, these cruise cars on the road, and they're often stuck at intersections. So based on that few interactions that I've had with a cruise car, when I bike around them and I see them at an intersection, I just try to like go around and go ahead and like make my left turn kind of like ahead of them, because I'm like, oh, they're probably stuck. They're just that cruise car that's stuck again. And then that I think is pretty interesting and kind of crazy that based on like my 3 interactions with a cruise car, I've decided to change my behavior. I'm giving wrong data to Cruise. Cruise is going to think that bicycles are just like moving around it now. But in general, these autonomous cars should think about how they are affecting and they're influencing other agents over short term and over long term, right? Like the long term version of this is thinking about the traffic problem, right? Like if I have a fleet of autonomous cars, like how would they affect my traffic congestion? How would they affect how cars make routing choices? And I think all of these are pretty interesting questions that require studying long-term repeated interactions between agents. So with that, I'd like to thank the group during the COVID time, and I can take any questions.
Thank you very much for this engaging talk. Yeah, I don't know whether, so that's the time that, people ask all sorts of questions if there are some pressing issues.
Yeah, maybe I can ask something. So, so really super interesting talk. Thank you. So you mentioned that you're synthesizing queries, right? So you meant by that, you have some mechanism to decide which pair of examples you're going to present the annotator, or is it like a classical pool setting of active learning that you have all the pairs and you decide which one to pick up? I'm not sure.
Yeah, that's a good question, and I kind of kept it vague because we have works that does both of them. So in the very first work, we are directly synthesizing this from continuous space. So basically, we are directly trying to, there isn't a pool that we are selecting queries from. We're actually synthesizing them from the space that they could be synthesized under that optimization. In follow-ups works, we have looked at settings where there is just we sample from that pool previously, and we just select from a library of these samples that are selected. Yeah, so we've kind of tried both, and although directly synthesizing from continuous space seems to be doing the right thing in some of these applications, from the application perspective, it didn't make that huge that big of a difference, doing the direct synthesis or selecting from a pool of queries.
Okay, thank you.
Great.
One quick follow-up question. Thank you, Dorsa. This was great. So I was looking at the figure where you had 0 queries and then on the right 70 queries. And I was impressed that for 0 queries, the car was still at least going forward. So I was curious about how do you initialize that policy over there?
Yeah, no, that's a good question. So it does start with some initial velocity. If you let it run, it goes outside of the lane and so on, because it doesn't have access to that. But yeah, it just starts with some initial policy and initial heading, and changing the heading with the dynamics that you're using. It's using the bicycle dynamics. So the dynamics, it's a little bit difficult, so it's not that easy to change that heading. So if you have some initial velocity, it just keeps going forward. But yeah, one could try other, and I don't think we tried any weird initializations. So I don't know.
Yeah, so does this mean, at least from your experience, that these active learning methods are in a way a second step, assuming you have a good initial condition, or would you advocate for them sort of basically from scratch?
That's a very good question. So we have, in that work that I showed, we started kind of from scratch from this initialization, but we had a follow-up work where we are combining this with learning from demonstration. So we start doing learning from demonstration because there's quite a bit of information in demonstrations. You get style, you get all sorts of informative things from demonstrations. They're just noisy sometimes. So one could basically do learning from a few demonstrations and then do a fine-tuning with active learning. So I think that is probably a better way of integrating active learning from preferences with some learning from some number of suboptimal demonstrations at the beginning.
Cool. Thank you.
Sorry.
Okay, very good. So I don't know whether there are any other questions.
Maybe I can just squeeze another question. So there's this issue of relying just on the more recent episodic memory in this setting. So right, because if the other party is responding to you, right, you really want to train representation that relies or kind of emphasizes more what was seen recently than what you've seen so far in general. I'm not sure if you cover this, or is this something that
No,
What
that's a
happens
very good question. Yeah. So in the first part, right, like we had this simple policy for the auto agent that was dependent on what the auto agent has done in the previous time step. So that's why even if we had like a short, like short trajectory, sequence trajectory, that was enough for like capturing what the policy of the auto agent is. But you can have more complicated policies of the auto agent, right? Like like what I was showing earlier in the air hockey example, it is really just like the game of like rock, paper, scissors, right? And then the best policy that you should do in rock, paper, scissors is to play random. So playing random is a lot more complicated. And like we wouldn't be able to learn like a partner policy for playing random because like even if like you give it a long history, right, it's not really like capturing like a representation for that. We have looked at more complicated policies than what I showed. So we're a setting where we're looking at a more like a longer history. And yeah, we need to have like a longer episode to kind of capture that. And our representation learning becomes like performs worse and worse over time. But I think it is like an interesting point to think about, like, is it easy to capture